Okay, looking at the second side, when we're looking at example 2, determining the next two terms in the sequence, when they let us know that it's a sequence and they give us just these outputs of 4, 12, 36, 108, we know we can assume that this is going to be the first term is 4, the second term is 12, the third term, the fourth term, etc. So they want us to find the fifth and sixth terms of each of these sequences. Feel free to draw these in if you feel comfortable, or if you don't need them at all, no worries. But so assuming that's the first step, we're going to know that the recursive goes like this. F of 1 equals 4, the first term is 4, and f of n is equal to f of n minus 1. Notice that as we jump here between these, from a 4 to a 12, from a 12 to a 36, from a 36 to a 108, we can see that that's multiplying by 3. What if you couldn't tell that it was multiplying by 3? What would I do in a calculator? In a calculator, I would put the second term in and divide it by 4. 12 divided by 4 would give me 3. I'd then get the third term, 36, and divide it by the second term. 36 divided by 12 would give me 3. 108 divided by 36 also gives me 3. By dividing, we can see what the multiplier is. So dividing the second term by the first term, the third term by the second term, etc., etc. So my recursive is going to also include that times 3. That times 3 can go in front or at the back. Next, for the explicit, how do we show that repeated multiplication? We're going to say this function begins at 4. We're going to say it's multiplying by 3 every time to the power of little tiny n minus 1. Why do we use an exponent in this explicit? Because to show repeated multiplication, we need an exponent of n minus 1 times. Okay, so there's my recursive and my explicit. How'd you do on those? To continue this pattern, we're going to go times 3 again. 108 times 3. It's going to give us 324. And then 324 times 3. It's going to give us 972. Obviously, feel free to use a calculator on those if needed. Okay, let's look at the next one. I'm going to go different color here. Let's go yellow. Okay, so for this recursive function, we're noticing that as we make these jumps, that it's multiplying by a 2. 5 times 2 is 10, 10 times 2 is 20, 20 times 2 is 40, but there's negative alternating here. So it is going to be multiplying by a negative 2 this time. So here I go with my recursive. The first term, f of 1, is 5. And then to get the next term, I take the previous term and multiply it by a negative 2. So you can do a dot negative 2 there. You can just put parentheses for it, whatever works for you. F of n equals, begins with 5 multiplying by negative 2 to the power of n minus 1. And again, where does this little 1 come from? Why is it an n minus 1? Because it's the first term. This 1 comes from this first term. Okay, and then so I'm just going to continue that pattern of multiplying by negative 2. And so 40 times negative 2 is going to turn into a positive 80. 80 times negative 2 is going to turn into a negative 160. How'd you do? Okay, last one. I got a lot of messages about this one because it is a fractional. How do I know it's fractional? Because it's decreasing. It's a decreasing function, meaning it starts with 243 and starts going down from there. How would I know it's fractional? Because if I multiplied by a whole number greater than 1, it would be an increasing pattern. So how do I get something to be smaller than its original? It's going to have a fractional multiplier. Now, a lot of students couldn't figure this multiplier out. So my recommendation, again, just like I mentioned in part A, is you take the second term and you divide it by the first term and see what it gives you. Take the third term, divide it by the second term. Take the fourth term, divide it by the third term, etc. When you do this, you're going to notice you get this like 0.67, 0.67. Anyone know what fraction represents that 0.67 repeated multiplier? You got it. It's 2/3. My multiplier, my fractional multiplier this time, is times 2/3. Okay, so let's go write it out. F of 1 is 243. F of n is equal to f of n minus 1 times 2/3. F of n begins with 243, fractional multiplier of 2/3 to the power of n minus 1. That's it. Now, how do I go to the future steps? I'm going to take 72, the fourth term, and I'm going to multiply it by 2/3. What does that mean that I do? It means I multiply 72 times 2, so that's going to give me 144, and then divide it by 3. So I'm getting 48. I'm going to take that 48 now, multiply it times 2, so that gives me a 96, and then divide that by 3. And again, feel free to use a calculator for those if you'd like. But so how do I multiply by 2/3? I times it by 2 and then divide it by 3. Okay, again, use a calculator if you want. I'm just kind of showing you the side work here. All right, anyone get that 2/3 on your own? If you did a times 0.67 in your work, you were close, but I do want you to try to get the exact answer of 2/3 in the future. Try to convert it to that fraction. All right, last but not least, we're going to graph two exponential functions. How do I know they're exponential functions? Because they've got their function name, f of x, and because they have the variable in the exponent. Okay, so how can I graph an exponential function? First of all, you might be able to just look at the story of the function. This is a function that begins at 3 and is doubling every step. Okay, and right here it shows us it's a time 1 function. So that means that these two little parts right here, this 1 and this 3, are our beginning dot. It's a coordinate pair 1, 3. And then from there, you're doubling with each step. So I'm going to go down and mark this graph out. If I'm going to be starting at 0, 1, 2, 3, 4, notice how I'm skipping. Okay, and since there's no context given, I'm just going to label this axis the x-axis, and this one's the y-axis. Now, how far up do I go on the x-axis? Well, we don't have a table to tell us, so we're kind of just winging it. So really, I do encourage you to try to have a table done before you graph any of these exponential functions, so you can see how far should we count to. So we've got x and f of x. We begin at time 1, 3. And then it's doubling from there. So doubling to 6, doubling to 12, 24, 48. Try to have at least 5 dots, and that should be good. So to get up to 48 on the left, 3, 6, 9, 12, 15, 3, 6, 9, 12, 30, 45, and then the next one would be 48. So it looks like we'd be good with that scaling. Okay, so let's go put those dots on at 1, 3, 2, 6, 3, 12, 4, 24, and 5, 48. This time, because this is a function, f of x equals, we are going to connect this function because functions are continuous. So functions are continuous. All right, how's your curve look? If you've graphed this exponential function correctly, it should look like a curve. Now this next one starts high and is then going to be halving. So picture this. This one's called g of x. This time it's starting high, and by the way, notice it's x minus times 0. So this is going to be a beginning at 0 function. So at time 0, we're starting way up at 3,000, and with every step, we're taking half of that. So half of 3,000 is 1,500. Half of 1,500 is 750. Half of 750 is 375, and then half of 375 is going to be a decimal because it's odd, so let's go look. $187.5. Grab a calculator so you can double check that. 187.5 is going to be our fourth dot. Okay, so how do I want to count? On the bottom, I'm just going to count 1, 2, 3, 4. And again, I'm just going to call this the x-axis because there's no other context given. On the side, I need to get up to 3,000. Let's try hundreds. 2, 3, 4, 5, 7, 8, 9, 10. There's 1,000. 2, 3, 4, 5, 6, 7, 8, 9, 10. That's only 2,000, so that's not going to be enough. So let's go maybe 1,500. Sorry, I was doing hundreds, maybe 150, I'm saying. So 150, 300, 450, 600, 750, 900, 1,050, 1,200, 1,350, 1,500, and that was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so our 3,000 is going to be right up here at 10 more. Okay, so that beginning dot is going to be at 0, 3,000. Next one's at 1, 1,500. Next one's at 2, 750. So 300, 600, 750 is right there. Next one's at 3, 375. Next one's at 4, 187. And again, this is going to be a connected graph because functions are continuous. Notice that in both these exponential functions, these graphs get close to the 0 axis but do not touch it. They're going to kind of go right along it and never touch. They're going to get infinitely close to that axis but never touch. So this is a continuous function. So it is connected. And don't forget this y-axis over here that I almost forgot. Okay, how'd you do? Did you have one increasing curve and one decreasing curve on that section?